Pretend you're on a deserted island. You can imagine it's a tropical island, okay? Spring break, tropical island. You're not like off in the North Sea somewhere in this terrible storm. Tropical island, but you would like to get home. A ship comes by with a captain who's just very kind of a crazy captain. He says, I'll let you on my ship if you've solved the following problem. Estimate the following quantity without technology, because you don't have any technology. No calculator, no internet, no Mathematica. Estimate, let's make it the cube root of 8.2 divided by, how about let's make it sine of 1.6 without a calculator. Okay, I should have said technology. Without a calculator, no technology at all. What could you do? You could use a linear approximation. That's what you could do. We did some linear approximations in Calc 1. Let's do a linear approximation in multivariable calculus. Here's the intuition. You say, boy, this would be a lot easier if that were just an 8 and that were, say, how about pi over 2? Note, I mean, you have to realize that cube root of 8 divided by sine of pi over 2 is a lot easier to estimate than our problem. Cube root of 8 is 2. Sine of pi over 2 is 1. The answer is 2. Okay. So you could say, hey, Captain, the answer is 2. No, sorry, I want something better. I want a better approximation. I want it good to, okay, 1 decimal place, and you got to be pretty sure of your answer, and or you have to be right. Why did I pick 8 and pi over 2? Notice that 8 and 8.2 are close together. And pi over 2, that's about 1.57. 1.57 and 1.6 are close together. That's why I picked, part of why I picked 8 and pi over 2, and also partially because the cube root of 8 and sine of pi over 2 are easy to figure out. So what do we do from here? Define a function. Z equals f of xy of 2 variables, such that when I evaluate that function, say when x is 8 and y is pi over 2, I get this quantity here. So I guess that means I need to do cube root of x divided by sine of y. X to the 1/3 over sine of y. That function's value at the exact point x is 8, y is pi over 2 is exactly 2. We want to know its value at 8.2, 1.6. Its approximate value without technology. This function, it's a function of 2 variables. It's going to have a graph. Graph is going to be some surface above the XY plane in 3-dimensional space. Don't know what it looks like exactly. It will be kind of a crazy surface in some ways. It'll have some vertical asymptotes at certain values of y. It'll go off to infinity because, right, you'd be dividing by 0. Close to y equals 0, close to y equals pi. Yeah, at y values close to, at integer multiples of pi, this is going to have some sort of higher dimensional vertical asymptote. Also near x equals 0, the cube root function as an ordinary function has a vertical tangent. So strange things are going on near x equals 0 as well. But we are kind of away from those points, so we don't have to worry about it. It's going to be some smooth surface near this point. Instead of using a tangent line to approximate a curve, how about using a tangent plane to approximate a surface? How do we find the tangent plane? Should make some sense that we want to use partial derivatives. That's what we need to do. Let's find partial derivatives. Reminding you of the various notations, there's z sub x, partial z partial x, or partial f partial x. I usually do say the word partial. You can say d. Partial f partial x or df dx. Most commonly, the function name with a subscript. And we don't always emphasize that this depends on x and y, but in general it does. Differentiate this with respect to x, treating y as a constant. So you're dividing by a constant. That just gets carried along. Bring down the 1/3 x to the negative 2/3 divided by sine of y, which could be rewritten, if you like, as 1/3, if you like, cube root of x squared sine y, if you want to write it that way. Partial of z with respect to y, its various notations. Some more sloppy than others. Probably the best notation is the final one here. Differentiate this with respect to y. I guess I'd need the quotient rule. Or I guess I could also write this as x to the 1/3 cosecant x of y. If I wanted to, maybe you probably don't remember the derivative of cosecant. It's the derivative of a cosecant of y would be negative cosecant y cotangent y. Maybe it's better to use the quotient rule. The top is a constant. It only involves x. I remember the quotient rule is low d high minus high d low over the square of what's below, where the d means derivative. Low d high with respect to y is 0. Very easy to make a mistake there. I almost differentiated that to get 1/3 x to the negative 2/3, but no, I'm differentiating with respect to y. Low d high minus high d low, the derivative of sine is cosine, over the square of what's below. Yeah, you are going to get negative x to the 1/3. You could write this as cosecant y times cotangent y. Maybe it's best to write it as cosine y over sine squared y. All right, what do we do with this? In Calc 1, the slope, the derivative, was the coefficient of x in your linear approximation. Evaluated at the point in question. Same kind of thing here. This is the slope in the x direction. It gets multiplied by x. That's the slope in the y direction. It gets multiplied by y, though I am going to write the formula a little differently. At an arbitrary point A, B, let's write it as at x comma y equals A comma B. The local linearization of the function f of x, y near the point AB is the function L of x, y, L for linear. You write it as z equals L of x, y. F of AB plus f sub x of AB, partial with respect to x evaluated at AB, times x minus a, plus the partial of f with respect to y evaluated at AB, times y minus b. For our example, AB is 8 comma pi over 2. This becomes f of 8 pi over 2 plus fx of 8 comma pi over 2 times x minus 8 plus fy of 8 comma pi over 2 times y minus pi over 2. We saw already that f of 8 comma pi over 2 is 2, right? That was this calculation up here. the note. Give us F. How about these partial derivatives at the same point? We haven't done that yet. This one would imply fx at 8 comma pi over 2 is 1 over 3 times 8 to the 2/3 would be 4. Right? Or do the cube root first and then square. That's not what this says to do, but we give you the same thing. Sine of pi over 2 is 1. This is 1/12. As a decimal, could you do that in your head? I think that's 0.083 repeating. I believe that's right. Does that seem right to people? I'm going from memory. I think that's right.
The last time.
Okay. How about Fy at 8 pi over 2? I can see just looking at it, it's going to be 0. Because cosine of pi over 2 is 0. So this simplifies pretty nicely. I'll approximate it here. To 2 plus 0.083 repeating times x minus 8. I guess if I do the repeating symbol, it's an exactly equal to. Plus 0. I mean, I got 0 there for the partial with respect to y, but it could have been something else. Could have been something non-zero, and then I'd have to take that into account. This is the equation of the tangent plane. In general, it depends on both x and y. For this example, it only depends on x. So, to get off the desert island, cube root of 8.2 divided by sine of 1.6 is approximately L of 8.2 comma 1.6. 2 plus 0.083 repeating. I don't even need to do 1.6 minus pi over 2. I was imagining I might need to do that. To do 1.6 minus pi over 2, 1 pi over 2 being about 1.57, giving me about 0.03. I thought going into this problem I might need to do that, but I don't even need to do it. I just do the 8.2 minus 8. And that's a 1/12. That's a 0.2 or a 1/5. Looks like the answer is 2 plus 1/60th. 2.16 is 0.167 approximately. This should be 2.0167 or so. Maybe you round it to 2.02. I mean, to one decimal place, it's rounds to 2. So maybe you did get off the island. But if you wanted more decimal places, hopefully it's close to 2.02. Okay, try it here. 8.2 to the 1/3 power divided by sine of 1.6. Oh, something's wrong. Oops, no, I didn't divide. That's why. 8.2 to the 1/3 power divided by sine of 1.6. 2.02, yeah, okay. To the next decimal place, it would be 2.01617, just like this is 2.017. What's the error in the approximation? The error is the actual value minus the approximate value. On the order of 7 times 10 to the negative 4. Pretty good. A small error. It's also got a relative error, where you take the error and you divide by the actual value at the point. Well, the actual value. The actual value was the 2.017389884. The relative error is 3.6 times 10 to the negative 4, though you'd want to convert that to a percent. 3.6 times 10 to the negative 2%. What would that be? 0.036%. Okay. A fraction of 1%. a small fraction of 1% would be the relative error. Why are we doing this? Got a technology. I'm not going to be on a desert island, right? Probably not. And even if I were, there wouldn't be a crazy captain coming by doing this to me. Okay. It's still good to see that it works, and this is what the author emphasizes. And the content of what I'm talking about here in the reading is still helpful for conceptualizing, understanding stuff that comes later. You should understand this. Let me rewrite this. So the idea here, the big idea, is that your function f of xy can be approximated by a linear function, L of xy, near some point AB, where the function f is nice. Then the question is, what does nice mean? Let's rewrite the formula for L of xy. It's f of AB plus f sub x of AB times x minus a plus f sub y of AB times y minus b. This is a good approximation near the point AB. So let's say, instead of saying near, let's say for x comma y close to AB, if f is quote unquote nice. But what does nice mean? It means differentiable. But what does differentiable mean? In Calc 1, differentiable means the derivative exists. In multivariable calculus, it's a bit more subtle because we got more than one independent variable. It is sufficient to be differentiable if the partials with respect to x and y exist and they are continuous near the point in question. So the partials exist and are also continuous functions near AB. That is good enough to say f is nice, it's differentiable. It's also known as smooth, or visually it's a smooth graph. Also known as locally linear. There are no kinks in the graph near that point. So if you zoom in on the graph near a point, you won't continue to see some kind of kink in the graph, some kind of corner, some sort of higher dimensional corner, which we will try to look at some examples in Mathematica of that, where smoothness fails. But we have to be more technical than this. And the condition that the partials exist in our continuous functions near the point is just sufficient for it to be smooth. It's actually not necessary. There are some smooth functions where the partials are not continuous, evidently. But they're weird. So we're mostly content with just that condition. In the book, in the reading in section 12.4, it gets into differentials. Another part of the big idea here is the idea of a total differential. And this is the weirdest part of this subject. I'm going to rewrite this approximate equation, getting rid of the L of xy, and also subtracting f of AB from both sides. Okay, I'm getting rid of the L of xy. I'm going to subtract f of AB from both sides and rewrite the approximate equation like this. F of xy minus f of AB is approximately fxab times x minus a plus fyab times y minus b. I'm going to continue rewriting this. with other notation here. I'm going to call this difference delta z, change in the z value for the function f, as I move from the point AB to the point xy. F changes in value by some amount equal to this difference, call it delta z. Sometimes you'll see it called delta f. Let's call it delta z. That's what the book does. X minus a is the change in x. I could call that delta x. Y minus b is the change in y. I could call that delta y. So with these new symbols, this equation becomes equivalent to delta z is approximately fxab times delta x plus fyab times delta y. Or if we prefer Leibniz notation, partial f partial x at AB, but I won't write the AB, times delta x, plus partial f partial y at AB, but I won't write the AB, times delta y. It's understood at AB when I write this, but I'm not actually writing the AB. Now we do something that gets the weird thing. We define two new variables, actually three new variables. We let dx equal delta x, dy equal delta y, and we let dz be this thing, partial f partial x delta x, but I'm going to replace the delta x with the dx because they're equal, plus partial f partial y times delta y, but I'm going to write a dy because they're equal. I put dots in there kind of by accident in the second case, so I put it over there as well. The dots are not necessary. It's not a dot product. It's a multiplication. Maybe you should write it without dots in there. I don't want you to think it's a dot product. It's not a dot product. Or is it? Okay. You don't have to write the dots in there. Since I already did, I'm going to go ahead and say these are ordinary multiplications. Ordinary, how do you spell ordinary? Ordinary multiplications of numbers. But I actually could write this as a dot product of two vectors. This vector dotted with this vector. And this vector has a special name. It's called the gradient of f. And it's got a special symbol, upside down delta f. Is that an upside down delta or is it an upside down triangle? Actually, the official name is neither. The official name for this thing is nabla, and I love that word. Nabla is the official name for that upside down delta. It's not a Greek letter. It's evidently a Hebrew letter, or Hebrew symbol at least. That means harp, I guess. I looked this up somewhere. That's what I was told. Because it kind of looks like a harp. Not really, but sometimes people make it fancier looking. Maybe they put like an extra line in there. Then it looks maybe a little bit more like a harp. And what's this thing here? That's just another vector with these new variables, dx and dy. Should I give it a name? Maybe the best thing to call it is dr vector. It's somewhat traditional to put the vector just above the r instead of the entire dr. I don't know that we always use this notation there, but anyway, it's good enough for the moment.
People never call the triangle a dell.
Yeah, you can call it a del as well. That I already said it a del as well. Yeah, some people do call it del, the del operator. But the official name for the letter as a Hebrew letter is nabla. That's my understanding, at least. I've read it in books. They say those kind of things. So what the hell's going on here? Effectively, we're creating a new function with these new variables. Dx and dy are new variables, just new names for new variables. And using these partial derivatives, we are creating really a linear function whose dependent variable we're calling dz. Is that what we're really doing? Yeah, you could say so. But aren't these sometimes called infinitesimals? Isn't like dx or dy, isn't that sometimes called an infinitesimal? Yeah. And what's an infinitesimal? Is it zero? No, it's not zero. An infinitesimal quantity is a positive quantity, not zero, but is smaller than any real number you can think of. So it's smaller than 10 to the negative 10, smaller than 10 to the negative 100, it's smaller than 10 to the negative 1,000,000, smaller than 10 to the negative Google power. Okay. And infinitesimal, yeah, infinitesimals don't actually exist. There is no such a thing as a smallest positive real number. You can always divide by 2 and get a smaller positive real number, or square it and get really a lot smaller positive real number, right? 10 to the negative 100 squared is 10 to the negative 200, which is 10 to the 100 times smaller than 10 to the negative 100. It's unimaginably small. They don't exist in the standard real number system. They do, however, exist in the non-standard real number system, which is called the hyperreal number system. And the study of infinitesimals is called non-standard analysis. And I'm not joking. I found a book in the library on non-standard analysis. I picked it up, opened it, looked at the first couple pages, put it back on the shelf. I don't think I want to learn this. It's a rigorous approach to infinitesimals. You can make infinitesimals rigorous. Newton, Leibniz, people back in the 16, 17, 1800s, they thought of infinitesimals intuitively, and that's kind of what we're doing. We do kind of imagine dx and dy to be so small that they're infinitesimally small, and dz would also be infinitesimally small. But in reality, as far as using this for the homework due after spring break, what we do is we use this to say delta z is approximately dz. The actual change in the function is approximated by, I'll just call it the approximate change. That is really coming from the L function up here. Coming back up here, I could rewrite this as f of ab plus dz. I could think of this entire thing as being dz. I think of that as dx and that as dy. As far as we're concerned right now, it's just a way of thinking about the linear approximation. The actual change that we want to approximate is approximated by the approximated change that comes from the local linearization. Let's do a simpler example than the one we started off with. Say f of xy is x squared times y. And the point in question, AB, is, say 2, 3. What's the local linearization of this function near this point? Also sometimes called the tangent. plane approximation in this context. We have to find the derivatives, fx as a function of x and y, differentiate with respect to x, get 2xy, and fy as a function of x and y, differentiate with respect to y, just get an x squared. Put all this information together, f of AB, f of 2, 3 is 2 squared times 3 is 12. Fx of AB is 2 times 2 times 3 is also 12. Use that formula there, use this formula here. Happens to be the same thing for this example, wouldn't have to be in general. Fy of 2, 3, using this formula, is going to be just 2 squared is 4. So near 2, 3, f of xy is approximated by L of xy, which will be f of 2, 3, 12. That's this number coming down, that 12 coming down there, plus 12, thought of as this 12, times x minus a, which is x minus 2, plus 4 times y minus b, y minus 3. 4 goes there. The 2 goes here, and the 3 goes there. So, for example, f of 1.8 comma 3.3 would be approximated by L of 1.8 comma 3.3. 12 plus 12 times 1.8 minus 3 minus 2 plus 4 times 3.3 minus 3. That'll be 12 plus 12 times negative 0.2. What will that be? That'll be negative 2.4. Plus 4 times 0.3. That'll be 1.2. Ultimately, we get 12 minus 1.2, 10.8 is our approximation for f of 1.8, 3.3. In actuality, f of 1.8, 3.3 is exactly 1.8 squared times 3.3, x squared times y, which is, with technology, 1.8 squared times 3.3, 10.692. Our approximation was 10.8. The error in the approximation is the actual value minus approximate value. 10.692 minus 10.8, which is negative 0.108. Errors can be negative when the approximation is too big. The relative error, negative 0.108 divided by the actual value, 10.692. About negative 0.01. Negative 1% for the relative error. In terms of the total differential, we would write, again, near the point 2, 3, dz would be what? Effectively, I'm using this part of the L of x function, replacing x minus 2 with dx and y minus 3 with dy. Dz will be 12 dx plus 4 dy. So if dx is negative 0.2 and dy is positive 0.3, like they were, negative 0.2 and positive 0.3, that implies dz is 12 times negative 0.2 plus 4 times positive 0.3. Again, negative 2.4 plus 1.2, which is negative 1.2. In other words, we're expecting as the point changes from 2.3 to 1.8, 3.3, that the function value will go down by about 1.2. That's how you want to conceptualize it. So as xy changes from 2.3 to 1.8, 3.3, f of xy goes down by about 1.2 from a value of, what was it, 12 to 10.8. This has other benefits when we get to doing more complicated kinds of integrals, including line integrals, for example. In section 12.7, it's going to give us, when we do the integrals in this context and think about the total differential in that context, it'll help us understand the integral better, intuitively, including line integrals and maybe ultimately surface integrals, for example. In section 12.7, there's an emphasis also on finding the equation of the tangent plane. Well, that's effectively just the equation of L, set equal to Z. Equation of tangent plane. For the same example here is Z equals L of xy, where L of xy is 12 plus 12 x minus 2 times plus 4 times y minus 3. And it's a little confusing. The book emphasizes writing this in standard form. And the standard form they write it as looks like this. Like that. Just rearranging the equation, subtracting z from both sides, and then rearranging to have a negative coefficient there. And they also think of that as a dot product. That's equivalent to the dot product of 12, 4, negative 1 with x minus 2, y minus 3, z minus 12 equaling 0. And this is a normal vector for the plane. That's the way the book emphasizes writing this thing. But it is essentially just the equation of the tangent plane, the graph, the equation of L of xy set equal to z. Okay, so I've tried to distill the most important things out of these difficult sections. When you read these sections, 12.4 and 12.7, they seem a lot harder than what we've done today, I think. So I've tried to distill the most important things for you to get out of it. I've skipped getting into nitty-gritty detail about what differentiability really means, because it's really hard. I've skipped this, though what I've talked about is related to this. I would encourage you to still read it. And this is kind of an interesting example here with a bunch of dx's and dy's all over the place to illustrate that definition. I'm not saying it's easy, but I think it might be worth your while to still read it and try to understand it. Okay, but the main things for your homework and exams are the kinds of calculations that we did to do today.